Hello everyone, welcome to this presentation. So my name is Emmanuel Kwasi Mensah and I'm a data scientist in an IT consulting firm in Frankfurt, Germany. In this video, I'm going to share with you a work I did in collaboration with Professor Mehdi Tulo on the topic, non-negativity and inequality constraint in a robust DEA. So a quick look at the outline I will share with you first on the motivation of this study, which is on uncertainties in DEA. Then we'll look at non-negative variables in robust optimization in general and also in the robust DEA. Then we'll also see how we'll deal with equality constraints in DEA for robust DEA analysis. Then we'll make application to banking efficiency in Europe. So the data environment analysis provide data-oriented approach to measure the efficiency of decision-making units. However, the measurement of this decision-making unit is marked in complex uncertain real-world environment. This uncertainty can affect the ranking strategies of the DMUs, and management decisions rallied on such efficiency can become unstable. In the optimization model, a small uncertainty in the data, according to Bentoy and Nemrowski, can make the usual optimal solution completely meaningless. Now, this uncertainty usually comes as a result of estimation errors, forecast errors, measurement errors, which are encountered at the time the data was being measured. Now, the effect of this uncertainty in the DEA model is such that the measured efficient frontier becomes disallocated from the true efficient frontier. In this case, the DEA model becomes sensitive to small data perturbation and as a result fails to preserve the efficiency of the DMUs. Now, if you look at this two input case, one output case example here, where we have exact data on the left and uncertain data on the right, the measured frontier and the true measured frontier projected from this exact data and uncertain data is such that the measured frontier is deviated or disallocated from the true frontier, and we have uncertainty in the efficiency result by this measured frontier. Now, in the optimization literature, there are two main approaches to model uncertainties. So we have the stochastic programming and the robust optimization. Also, in the uncertainty literature, we've had different approaches. We have the fuzzy DEA, which is proposed by Segunta in 1992. We have the imprecise DEA by Cooper et al. In 1999, which takes care of interval, ordinal, and ratio data. In recent times, in 2008, Sajadi and Omrani introduced the robust optimization into the DEA, where now we have the robust DEA. Now let's look a bit into the robust optimization. So the robust optimization relies on the worst case analysis. It provides a solution that is evaluated using the realization of the uncertainty that is the most favorable. And this is done through an alternative formulation of the nominal problem called the robust counterpart. Now, two things are considered in formulating this robust counterpart. So the first one is that the decisions on the uncertainty parameters are made here and now, which means that they are modeled before the actual data reveal itself. The second one is the uncertainty set, which is often constructed based on information or assumption of the uncertain data. Now, at the heart of the robust optimization is the uncertainty set. There are different uncertainty sets which are used in the literature. The common one are based on the structure or geometry of the set. The first one I'll talk about is the Bose uncertainty, which is given in the interval form. Now, this uncertainty set was proposed by Soster. So Soster was the one that proposed the robust optimization in the literature in 1973. However, due to the ultra-conservative solution using this Bose uncertainty or the interval uncertainty, the solution sometimes become very bad. Now, Bentoy and Nemrowski in 1998 considered an Elipsoda set which is able to control the conservatism of the robust solution. In the case here, because the sub-problem of the robust counterpart is optimized over quadratic constraints, this leads to second-order cone programming, which means that we have introduced nonlinearity into the robust model, which becomes sometimes a bit difficult to solve. We also have the budget or gamma uncertainty set, which is proposed in the literature by Beximas and Sim. And this uncertainty set also helps to control the conservatism of the robust model. The gamma uncertainty basically is a polyhedral set that encodes budget of uncertainty in terms of the cardinality constraint. And it controls the number of parameters that are allowed to vary from the nominal values. And in this case, it provides different trade-off between optimality and robustness. The disadvantage is that the assumption made on the uncertainty data, uncertain data is, they must be independent and also symmetric. Now, we also have the polyhedral uncertainty set, which provides flexible structure to model uncertainty. However, it has the difficulty in deriving optimal polyhedral coefficient for the robust counterpart. Now, in the robust literature, the robust counterpart are usually proposed for general decision variables, which can assume both either negative or positive values. The problem here is that where we have optimization problem that involve only non-negative decision variables, such as in the transportation program and the DEA, this general robust counterpart proposed in the literature present unwanted parameters and variables that demand more computational resources. So we formulate an alternative robust counterpart, which we call here the reduced robust counterpart. And in this reduced robust counterpart for non-negative decision variables, we have removed the redundant constraint and auxiliary variables, which helps to save computational resources and also time. Now, the advantage of this reduced robust counterpart can be seen by this comparison when we consider the source test model, which is based on the strict robustness concept. So in this model, when we formulate it in the standard form, we have n plus 2k plus 2n constraint. Then we have n plus k non-negative decision variables and also n plus 2k plus 2n slack variables. Now, the case when the reduced robust counterpart is considered, this model involves only m constraints, n non-negative decision variables, and m slack variables. Now, similarly, when we consider the robust approach of Beximas and Sim in their paper, The Price of Robustness in 2004, again, when we transform this model in the standard form, we're going to have n plus 3k plus 2n constraint. We have n plus 2k plus n non-negative decision variables and n plus 3k plus 2n slack variables, which are involved in the model. However, when we use, again, the reduced robust counterpart, we will have only n plus k constraint, n plus k plus n non-negative decision variables, and n plus k slack variable. So you see the complexity of the models here and the iteration count per operation in solving each of the models, that is the general robust counterpart and the reduced robust counterpart. Now, for a tractable robust counterpart, efficient running of the optimization algorithm depends on the model structure and the iteration count required to solve the problem. So where the iteration count, which depends on the number of decision variables and the number of constraints in the model, is high, then it means that we're going to need a lot of time and computational resources to solve the model. In the reduced robust counterpart, you see that the number of variables, decision variables and constraints are reduced, and this involves less iteration per operation as compared to the general robust counterpart when we are solving problems with non-negative decision variables. And this you can see for the Bose uncertainty set and also the polyhedral interval uncertainty set. So a quick example from Bazara, where we have a problem with non-negative decision variables. Now, the nominal values of this problem are 2, 1, 1, 1, negative 1, which comes from the first and the second constraint. The optimal solution is, as you see here, and we have the objective function value to be negative 28. Now, let's assume that the nominal values are 10% accurate approximation of the true vectors of the coefficient. Now, for the first constraint, we'll consider the first term and the third term to be the uncertain items, and also for the second constraint, we'll consider the second term. Now, when we formulate the robust counterpart using source test approach, this is what we got, which will involve a situation whereby the decision variables will have negative variables here, which may not be wanted. Now, when we consider the reduced robust approach, we will have this model, and what we see is that the robust reduced counterpart removes the redundant constraints and auxiliary variables. And again, you can see that the model complexity has reduced. However, we have the same solution, which means that the optimal solution is not sacrificed. And to see this, a numerical example produce this result, where we have the optimal solution for the general robust counterpart. The objective function values are here. Then we also have for the reduced robust counterpart, the objective function values are here. You see that they are both equal. It means that in reducing the model complexity for problems with non-negative decision variables, we have not sacrificed the optimal solution of the model using the reduced robust counterpart that we propose. However, we've been able to save a lot of computational resources. Now let's take a look into the robust DEA literature. So the first model, which was proposed by Sajadi and Omrani, is what we have here, where they considered for this constraint here, the decision variable to involve non-negative variable. And we all know that the weight of the output weight is non-negative. So for this particular constraint, you see that this constraint where we have negative z less than or equal to UR is not needed in the model. Another thing that you see is the normalization constraint, which is an equality. And in robust optimization, we do not consider equality in the constraint. We do not consider uncertainty in the equality constraint because this leads to infeasibility or restricting the constraint. Now, because of this, it became difficult for the researchers to consider uncertainty in the normalization constraint. And what we can do is to look at the normalization constraint, how we can formulate it into an inequality constraint. And we do so by using this model that we propose. So we propose an alternative model for the CCR where the normalization constraint is an inequality form. And the proof of this model is using the dual model of these two models. So you see that per the duals, because the constraint here is equality, the decision variable here, theta, is free in sign, whereas for this particular model, we have for inequality, the variable assigned to this inequality constraint become greater than or equal to 0. And when you compare these two models, the only way this model become feasible is when this theta assumes only non-negative variables. It means that theta cannot be negative. And when theta is greater than or equal to 0, then we have these two models to be equal. And again, when the dual models are the same, then we will have the premium models also to be equivalent. Indeed, when you consider a numerical example using the equality constraint and the inequality constraint, you find the optimal solution of these two models to be the same. Now, using this equality constraint that is reformulated to inequality constraint, then we can provide uncertainty in the normalization constraint for the input variables. And also, again, we consider the reduced robust counterpart, and we remove that of the non-negative decision variables, which was initially used for the output weight. And we get this new model. So this proposed model involves no redundant constraint and also auxiliary variables, whereas we've been able also to consider uncertainty in both the input and the output. Now let's look at an application of our approach to 250 banks in Europe. The objective here is to compare the complexity of the robust DEA and the reduced robust DEA using this data, and also we try to rank the performance of the banks using the robust reduced counterpart DEA model. Now, a quick glance at the data, we select the 250 largest banks in Europe in terms of assets, and this includes banks such as the PNB Paribas, the Deutsche Bank, and HSBC Bank, and etc. Now, the data is obtained from the bank scope database. So we group this data into 5. The first one consists of 5 DMUs. Then we have the next one, which is 100 DMUs. Then we perform an attrition count, for the robust DEA and also the reduced robust DEA. And as you can see for the goal here, we want to understand the numerical difference in the computational complexity between this robust DEA and also the reduced robust DEA as the size of the problem increases. And as you can see, as the size of the problem increases, the attrition count for all the models increases. However, for the reduced robust counterpart, you see that we've been able to reduce the attrition count involved in solving the model. Whereas for 50 group of DMUs, the attrition count in the Sajadi's model, Sajadi and Omrani's model, is 333. Using the reduced robust DEA, we have 233 attrition count, and we have 30.3% reduction. And you can see the same analysis for the other group of DMUs, 100 up to 250, where in each case you see that the percentage, percentage of reduction for the for the reduced robust DEA. So in all, for the 250 DMUs, you can see that we have reduced almost 50% of the attrition count that save computational cost and time that would have otherwise be involved in the normal DEA, robust DEA model. Now we also rank the efficiency of these robust DEA models and compare the result of the efficiencies. So we consider efficiency perturbation level of 1% and 5% for each of them. And under the robust DEA, we have these efficiency values. And for the reduced robust DEA, we have these efficient values. And as you can see, the ranking under the robust DEA and the robust DEA are the same. The efficiency values are the same, which goes to re-emphasize what we had in the robust optimization, that using the reduced robust DEA, the optimality is not sacrificed. So the robust efficiency result from the reduced robust DEA is the same as that of the robust DEA. The advantage, however, here is that we have been able to reduce the computational cost by considering reduced robust counterpart for problem with non-negative decision variables such as the DEA. So these results basically can be seen in this paper that we published in Computers and Industrial Engineering, Robust Optimization with Non-Negative Decision Variables. So if you want to see more into what we did, you can look for this paper. And again, you can also look into this thesis that I did last year, 2019, where I considered the general framework of robust optimization in data environment analysis. So this is published, and you can find the topic, robust optimization in data environment analysis, extended theory and applications. Thank you very much for your time.